All right, so what I'm going to do now is I'm going to flip back to my iPad here because I want to talk about the program we're going to run on this instrument. So a really nice thing too that this program or that this instrument does is you literally can set it up to run a program. So you guys were the program when you did it in organic chemistry because you had to know when you were going to change buffers, you had to change your tubes, all of that stuff. This is sort of done for you, okay? So I want to just kind of highlight what this program is that we do. So I'm going to tell you what the steps are. It's not a super user-friendly like program. So I'm going to tell you what the instrument would say, but then we're going to more importantly talk about what it means. The first thing it's going to say is collect all. So these are literally lines of like program that you see. It's going to say collect all. It's going to say 3 minutes, and it's going to say 1 milliliter per minute. So that's what the instrument will say in red. We're going to put under here in blue what is really happening. This program that we're going to set up is going to collect all fractions. That's what collect all means. And just to step back for a second, so again, if we were in lab, I would have had those tubes that had those 5 proteins, the esterase, the glucose oxidase, all of that. I would mix them all together, and then I'd say, we're gonna use the FPLC to separate them back out, okay? So here's the program that we're gonna have the FPLC run so that we can isolate them. So collect all fractions. That 3-minute time period means stay at each tube for 3 minutes. And then this 1 milliliter per minute is our flow rate. This is really the speed that our mobile phase is going through the system. And taking these two pieces together, if we are spending 3 minutes at each fraction and we're going at 1 milliliter per minute, this tells us that each fraction is going to be 3 milliliters in size. So this is just kind of the preliminary information that we need to start our program with. Do you want to collect all or just some fractions? How long do you want to stay at each fraction? And importantly, what's your flow rate for your mobile phase?
What is a fraction?
So a fraction is the test tube. So when we're collecting test tubes. So the next steps all represent time periods that we're going to have. So from 0 to 3 minutes, we're going to just use buffer A. Okay, so what this means is for the first 3 minutes of our experiment, we're going to only draw from buffer A. And I want to make sure to tell you what buffer A is. So buffer A is 25 millimole tris, pH 8.1. Now we're going to have, at 3 minutes, we're going to have an alarm go off on the instrument, okay? Because what's happening right now, I'm going to flip back to this page for a second. When I am starting this program, my mixture of 5 proteins are sitting in this sample loop. So I'm having, and remember, I'm starting out with 100% buffer A. So here's the pathway that my instrument is taking. I'm pulling from buffer A, I'm coming through the mixer, the pump, and then I'm going through and picking up passengers, and then I'm continuing on through here. So that's the path that I'm taking. Now the problem is, from a bus standpoint, we don't want to continue to stop at the bus stop after we've picked up all the passengers, right? That's wasteful. We're driving on more road than we need to. So at 3 minutes, I have picked up all the passengers that I need. So that alarm is just to remind me to change this so that I stop stopping at the bus stop. Does that make sense, or do you need me to, anybody want me to go over that again? So now, after my 3-minute alarm, I'm no longer going to be stopping at the bus stop. I'm just going to take a main line through, and I'm collecting all my fractions. Now, why is this important? Well, as we'll see in a little bit, we're going to coordinate the time that the instrument thinks something happens with what we're going to be collecting from our fractions. And if we have extra road that we're traveling through, our time sequence is going to be off just a little bit. Just like if the bus driver was continuing to stop at stops he didn't need to stop at, the bus is going to be late. So for that reason, if we don't need to be going to the bus stop anymore, just stay on the main line. Okay, so that's why we have this alarm. So just kind of highlighting what happens here is we are going to disengage our sample loop. We're telling the system to stop stopping at the bus stop. There's no more passengers. We've picked up all our sample, and you are going to be late. Which means, from an experimental standpoint, we're going to think something's happening at a certain time, but we're going to be off because everything got backed up. All right, there's only 3 more steps in the program. From 3 minutes to 13 minutes, we are going to go from 0 to 50% B with what we pull up from our samples. So for the next 10 minutes, we're going to be increasing the concentration of B in our mobile phase, in our solution. So it is important that I highlight what buffer A and buffer B are. So again, here's what buffer A is. And so I'm going to highlight down here what buffer B is. So buffer B looks a lot like buffer A. It's going to be 25 millimolar tris, pH 8.1, but then it also has 500 millimolar sodium chloride. So really we can say that buffer A is no salt and buffer B is high salt. And this will become important a little bit later when we kind of learn about why salt might be important here. Questions?
Every time that you use this machine, do you always use the same 2 buffers?
It's a good question. No, you can change the buffers that you want. It depends on what you want to be changing over time. So in this case, I want to be changing the salt concentration over time, but maybe you want to be changing pH. So you might have a buffer A that's high pH and then a buffer B that's low pH. And then you can create a pH gradient as you go along. So it totally depends on the kind of bells and whistles you need to have. And we'll get to those a little bit later after our break. All right, then we're going to have 13 minutes to 19 minutes here. Now we're going to change and we're going to go pure buffer B. So again, what this means for the next 6 minutes, we're going to only draw from buffer B. And this little program is only 25 minutes long. From minutes 19 to 25, we're going to go back to 100% buffer A. So only draw from buffer A. Okay. So the last thing I want to go through here, and then we're going to take probably a 15-minute break, give you guys a bio break with whatever you might need, whether it's a little food, a little bathroom, whatever you might need. I want to highlight what we're going to see in terms of output from this instrument. So this is how this instrument in this process is very different maybe from an organic chemistry column chromatography. You guys had to constantly do like TLC plates and all kinds of stuff like that to monitor what was going on. This actually is connected to a computer and gathers data, and we get something that's called an FPLC trace. And this is a double Y plot, okay? And as we started this morning, I went, oh, yeah, we haven't learned about double Y plots because we didn't do our dry lab on how to use Excel because we were going to sort of push that back. So if you don't know what a double Y plot is, a double Y plot basically has the same X variable and two different Y variables. So if we draw a double Y plot here, our X variable is going to be time. So time in seconds that's passed. On one axis, we're going to show the absorbance at 280. And so a blue line is going to be our absorbance at 280. And then we're going to show conductivity. And that's going to be a red line. So I'm going to map some important points on here, times where we do something different in our experiment. We changed what we did at 3 minutes, at 13 minutes, at 19 minutes, and then we were done at 25 minutes. So if we go back and sort of look at this, which you guys have written down already, at 0 minutes, 3 minutes, 13 minutes, 19 minutes, we did something different, right? So I'm going to start with my red color here, and I want to think about saltiness of the solution. So when I start out, I'm pure A. So there's no salt in A. So does it make sense to everybody? I'm going to have a nice flat line there. And then what happened at 3 minutes? Well, I started adding in my buffer B, which was a salty solution. Now, I did it gradually over the next 10 minutes. I increased my saltiness gradually. Does that make sense to everybody? And then I changed again and I said, no more gradual. You go up to 100% B right away. So I'm going to jump up to super salty and I'm going to stay there for the next 6 minutes. And then I said, you know what? Let's go and go back to no salty and do it quickly and then stay like that to the end. So does that make sense to everybody? I was measuring the salt in the solution that was driven by these directions. That's what this should look like. Everybody with me? All right. So the last thing is to realize that when we are doing this experiment, and let's say we're doing this experiment with our 5 proteins, okay? Each of those proteins is going to have a different affinity for my column, okay? So what I might end up seeing here with my absorbance at 280 is something that looks like this. I might see 5 peaks here. And if I label these A, B, C, D, and E, I want to ask some questions about these. And then we're going to take a little break for a little bit, give you guys a bio break here. And then we're actually going to return back to part of your post lab is to actually take the data from the real purification we did, which is going to look very similar to what we have here, and protein. Let me ask you guys a quick question first here. And I want you to answer in the chat. Which protein A, B, E has the greatest affinity for my column? So think about it for a minute, then let me know in the chat what you think your answer is. Which protein, A, B, C, D, or E, has the greatest affinity for our column? No one wants to be the first to provide an answer.
What's the column made out of?
In this case, it won't matter. It won't matter. We are going to get to that. That question will matter, but to just answer the question, which protein has the greatest affinity for the column, you don't need to know that for right now. But it was a good question, but you don't need to know that to answer. Is that everybody? 1, 2, 3, 4, 5, 6, 7. I think I need one more. There we go. Let's see. Connor, you are right. Was it a guess or what's your thought process?
It was kind of like my best educated guess. So like peak D was like the ion concentration with the salts, and A was buffer.
You know what? So you might start again because you got cut off a little bit. Turn off your video just for a second because we might not have the bandwidth to do both video and audio. So I want to be able to hear you. Go ahead.
Okay, so pretty much my guess was that peak D was with the high concentration of salts and A wasn't. So based on the peaks, E was kind of in the middle. And that was really my thought process for it. Not sure if that's the right way or not.
So I think for some people, I saw a lot of A's. So some people are like, it's got to be either the first or the last, but I don't necessarily know which one. So some people said D with a question mark. Corinne and Kate, you were both like D with a question mark. So, and part of that maybe is my inability to like freehand draw very well. So maybe you're like E is past the point of the high salt. So maybe not. But in general, the thing that has the greatest affinity for the column is going to be the thing that comes out last. Doesn't matter what the column is. We'll get to those details later. But whatever comes out last, remember how this works. We've got stuff that's kind of coming through our pipeline, right? If I come back here for a second, we've got stuff that's coming through our pipeline, okay? And let's imagine that we've gone and picked up everything. Once we come to the column, depending on how much time you spend hanging out in the column is going to determine when you come out, okay? And when the UV detector detects you. So if you spend a lot of time partying and hanging out in the column, you're going to be the last to leave and get recognized by the UV detector. So Andrew, that was a really good question to ask what the column's made out of, but truthfully, it doesn't matter to answer this question. Whoever interacts with the column most is going to come out last. Does that make sense?
I had it pictured kind of like a TLC plate, like the more it binded to like the actual plate itself, like I don't know. I think
that's absolutely right, because TLC plate is the same thing. Your TLC plate is your stationary phase, and right, a TLC plate is really the same material that you have in your column. It's silica, right? You're just looking at it in a little micro mini version on a plate, okay? But the same is true, that the speed that things will move through has to do with their affinity for that column. And so things that migrate with your solvent front don't have very much of an affinity. Everybody with me? Okay, I'm going to show you something real quick, and then we'll take a break for a minute.